So this is my second attempt to explain what generative adversarial networks are. I did some theoretical explanation at a little meeting in the IoT center in Munich once last year. So I have learned a bit more about it, and I want just to update you. I also have a working implementation in a Jupyter notebook using the Keras deep learning framework. So actually, to understand a GAN, we first need to understand the convolutional network. So a convolutional network is basically a deep learning neural network specialized on image classification and other computer vision tasks. So when I'm talking about convnets here, I'm especially talking about 2D convolutions. And you see here a bit of Bayesian expressions. So for example, you have here d of cat given vector x, and the vector x is basically nothing else than the image, or in this case it's a matrix. So given the matrix x, the probability d of seeing a cat is 1, and the same holds for the second example. Given another matrix x, which resembles a dog, of course, the probability that it is actually a dog is 1. So that's just a repetition of convnets. So let's have another example here. We have here now two images, and one is a real image and one is a fake image. I'll let you guys guess which one is real and which is fake. So you can clearly see that the first one is a real image, and by the way, this is me together with our IBM CEO Jeannie Rometty, which I met once in my life. That was a special moment. So hi Jeannie. So the second image is a fake image. So I've never ever met Arnold Schwarzenegger. So you see here the discriminator's task is to determine whether an image is a real image or a fake image. That's the whole idea. That's the only job a discriminator needs to do. And of course we are training the discriminator with a label, okay? So we show the discriminator a real image and we label it with 1 for real, and we show the discriminator a fake image and then we label this fake image with 0 for fake. So in order to generate those fake images, we use a second neural network. That's the generator. So you see here, from jumping from this slide to the next slide, that the fake image is actually generated by a convnet as well. So this is not an ordinary convnet, this is some sort of a reverse convnet. Especially the pooling layers which you have in ordinary convnet are replaced by upsampling layers. So what this guy does is basically taking this random latent vector which you see on the left hand side, and using the some sort of reverse convnet is generating an image. So now if you have random weights on the generator and of course a random latent vector, then your fake image is nothing else than random noise, which we will see later in a practical example. But it turns out we can now train the generator by using the discriminator. So the idea behind this is that the discriminator D is trained on real and fake images. The real images are coming from a pool of real images, and the fake images are coming from the generator. So this is the generator here. And the idea now is to create a joint model, and that was the thing which I've been struggling before. So I didn't really know how this joint model is trained, but now I have a more clearer understanding. So you're creating a joint model between the generator and the discriminator, and you are somehow training them in conjunction. I will come back to that later in the code. And then we optimize the model. And the idea is that the discriminator gets better and better in distinguishing between real images and fake images, and on the other hand, the generator gets better and better in creating fake images. And if they are both more or less on the equilibrium, we have a very, very powerful generator which can basically generate very realistic looking images from a random latent vector. So if you don't understand what I'm saying, let's have a look at some applications. And with applications, I mean more or less some toy examples. So I haven't found really interesting applications so far, but I'm sure there are. So this is one example. This is a data augmentation, and I think that's the most interesting use case for GANs. So you see here those pictures, and some of those are real pictures and some of those have been generated by the generator part of the GAN, and you can clearly see that it's very hard to distinguish. So that's pretty awesome. You see here, that's called property transfer. So what you see here is you have an image of someone who has some clothes, and then you have the ground truth, so that's the same person but in another position, and then you have a position matrix, and the GAN can now turn this person according to the position matrix. That's pretty impressive. You see here some errors at the generated image, but still it's doing a quite good job in my opinion. You can, for example, transfer properties of images. So you have then zebras which have the skin of a horse, or you have a horse which have the skin of a zebra. Or you can extract objects from images. So for example, you can extract clothes from persons. Pretty impressive. Then here's an example of image sharpening. So if you train the GAN with artificially blurred images and the GAN is actually getting an objective in creating sharpened images, it will also work. Okay. And then another important and interesting feature here is that we can generate from a semantic map a real image. So usually in self-driving cars you do it the other way around. No, you have an image and you are generating a semantic map of those, but here you can create with a semantic map and a random latent feature vector together, you can create a real looking image. And since the generator is trained in maximizing the, let's say, or minimizing the amount of errors which it does against the discriminator, it will learn only to create realistic looking images. So for example, if you change the feature, the latent feature vector, and feed the same semantic map into the GAN, into the generator, maybe only the color of a car will change. So you won't generate an image which has weird properties. It's always looking like a real image. That's the property of the GAN. Then that's a pretty obvious application where you just generate images from captions. I think that's pretty old hat. No, that's from 2018. Image inpainting, so you remove parts of the image and the GAN can basically complete the image again, and it's doing a quite good job in some of the images. So you see here at the boat, it's not so nicely, but for example at that fish in the water, it's definitely doing a really good job. Music generation, I haven't heard so many nice sounding examples, so I don't want to play those now, but still that's something which is in the pipeline. And yeah, that's basically it for the slides here. If you are interested in learning more about data science, machine learning and AI, just go to nopanic.ai/data science, and you can get a Coursera certification. And if you are fast, you can go to ibmcoders.influitive.com/challenges. I will put the link in the description, and you take the applied AI challenge. So where did that go? You click on the available challenges and you see the applied AI challenge, and just fill out the quizzes and you get a promo code in order to get a free Coursera subscription for 1 month to complete those courses. And of course, please don't forget to check out my books, which I've written on Apache Spark 2.x. So I'm explaining all the details about the internals of Apache Spark as well, and also how you can apply machine learning and deep learning on top of Apache Spark using different frameworks like SparkML, Deep Learning for J, SystemML, and so on. Okay, so we are now here in a Jupyter notebook, and the author of the code is Eric. So thanks a lot, Eric, for open sourcing this under the MIT license. First of all, we need to check whether we are running on at least TensorFlow version 1.12, which we aren't. So I have here run this upgrade command already, since it takes some time. And after we restart the kernel, we should be on TensorFlow 1.12 at least. And if this is the case, then we can continue. So let's have a look. Okay, 1.12, the correct TensorFlow version. So we run some imports. This is straightforward. And then we initialize some variables. So we are here actually creating a GAN and a discriminator and a generator network. And the generator network will learn how to create MNIST digits. So for those who are familiar with MNIST, it's pretty straightforward. You have this 28 by 28 pixel handwritten digits and only one color channel, and the latent dimension I will show you later where it is used. So that's the random input vector which is fed into the generator network. And then of course the image shape is image rows, image calls and channels, so 28 by 28 by 1. So now we are creating the generator. So this is an ordinary simple sequential Keras model. And the first layer is a dense layer, because this first layer needs to take over the data coming from the latent input vector. And then it's getting more interesting. So we have here a upsampling 2D layer. And as usually in Keras, if you are not in the first layer, all the intermediate neuron sizes and connections are automatically computed for you, so you don't have to care about those. So you say here, from this shape here to this shape, Keras is doing the job for us. So it creates all the weight matrices for us, so we don't have to think that much about it. The idea of upsampling, of course, is to go from a lower dimensional representation to a higher dimensional representation. So that's basically the inverse of the pooling layers we have in ordinary convolutional neural networks. And here we apply some batch normalization and another upsampling, and that's basically it. So it's some sort of a reverse convolutional neural network, and then we just return this model. Okay, so the second is the discriminator. So the discriminator is really an ordinary convnet. So we have those convolutional layers, leaky ReLU, activation function, dropout, convnet, batch normalization, and so on. And at the end, of course, we have a flatten, and then we have here a dense layer as output layer. So a dense layer is a fully connected layer which has only one neuron. So that implies we need to use the sigmoid activation function. So that's recommended if you have only one neuron for a binary classification task. Otherwise, in multi-class classification, of course, you would use softmax activation function. So then let's actually run those. So that's all straightforward. So we define the optimizer. This is Adam with two parameters here, and then we build a discriminator. We compile the discriminator here. We use binary cross entropy as a cost function. This is perfectly fine because it's a binary classification problem to classify between the real and the fake images. We put the Adam optimizer here, and then the metric is accuracy. Then we build a generator, and now as input for the generator we have this latent dimension which we basically sample. And then we have here, that's the important part, the model. So we create now a model out of the generator and the discriminator, and that's the thing which was confusing me the most. So how is the generator and the discriminator trained at the same time? And it turns out that it is trained alternatively. So in one iteration, this discriminator's weights are fixed and only the generator weights are adjusted using a gradient descent update step, and the other way around, the generator's weights are fixed and the discriminator is basically trained using gradient descent. So that's alternating training. So let's run this cell here. And we see here those are the summaries of the generator and the discriminator, and then we need just to save the image to a folder after a couple of epochs, just to make sure we can basically track the progress. And then we define the training function, so we are training for a couple of epochs, I think 4000, and that's basically it. So we need to create a folder called images, and now we can start training. So we are pulling the MNIST data, and then the Keras neural network should actually starting training. So we are at epoch 0, and you see it's pretty damn slow. So there's no chance in finishing that on time, because at least accuracy is going up, but you see here, if you have 4000 iterations and at that pace, it's pretty hard. Let's have a look. Stop watch. How long it's actually taking. So whenever I see the next epoch, I will start it. So it's start, and then I will stop it to get a rough idea. Stop. So it takes nearly 5 seconds per epoch. That means 4000 by 5, that's 20,000 seconds. So 10,000 divided by 60, that's 5.5 hours. So that's definitely not something we want to do. So let's actually change the environment. So we leave this notebook here now, and you see here this green circle means that actually the kernel is still running in the background. So what we do is we stop the kernel. So now the process is killed and the training stops. And now what we do is we say change environment, and we go to 16 cores and 64 GB of main memory, and then we start over. So you see here it's consuming 8 capacity units per hour. That's on the high side, but we have 50 for free per month, so we can train at least for like 5 hours, which we don't need, hopefully, no? So again, we need to double check whether the TensorFlow version is correct. I don't think so, so we need to upgrade it. So the thing why we are always on that old version of TensorFlow, the reason is because whenever you change the environment in the background on our Kubernetes cluster, a new set of Docker images is provisioned, and they are just taken from a template, and in that template currently we have version 1.3 pre-installed. Therefore we always need to run the upgrade command, and it actually only takes effect after you have restarted the kernel. So that means we're actually waiting until this command finishes and restart the kernel, and then we should have version 1.12. Okay, this is done. So you see, if I re-execute this cell, we still have 1.3. So let's restart the kernel. So you see here restarting kernel, and then the output should disappear, and now we should get 1.12. Okay, so again we run the imports, we initialize generator, discriminator, and so on, and then we start training. Let's see if it's faster. Oh wow, that's definitely faster. So that's pretty cool. So see, that's one reason I like being in the cloud, because for let's say those compute intensive tasks, from a drop down you just take a couple of more CPU cores and you are basically running much faster. So you see here it's around half a second instead of 5 seconds per epoch, and that's definitely something where we can live with. So let's actually wait for another 3900 epochs, and then let's see what happens afterwards. So we are almost done. Only 8 iterations are missing, epochs, sorry. So that was far faster. I think it took 20 minutes instead of 5.5 hours. And we should see a couple of images. So let's actually print the first and the last overview of the generated images from the generator. So you see, as expected, if you randomly initialize the generator network, you get some random noise from a random latent vector. But if you train the GAN against the discriminator, then you see here, those are the images created by the generator part of the GAN using latent feature vectors. So that's really cool. So yeah, that's basically it. So if you have any questions, then just put those into the comments and I will try to answer. Thanks a lot for watching. Bye.